Welcome back to Chem 4300. In this video, we're going to be doing a short review of complex number notation. Now, complex numbers appear in a lot of physics problems that involve oscillatory motion. It's a very convenient mathematical tool to simplify the equations into a more compact form where we can keep track of amplitudes and phases that are involved in this oscillatory behavior. To see how this works, let's take a look at a simple example. Let's just take a vector, let's say that's moving counterclockwise around the origin like this. So this vector r at some initial time is along the x-axis. So if we were looking at this as a function of time, it would start out at the maximum amplitude and it would oscillate with some frequency that's determined by the angular velocity of this vector moving around here. Now, excuse me, if we were looking at the y component, then at the initial time it would be start out with 0 along the y direction projection, and then as we rotate around, then that projection on the y would increase and it would oscillate as it goes around counterclockwise. Now, to describe this mathematically, you might say, well, I'll just write down that the x component of the vector is r cosine omega t and the y component is r sine omega t, and that would work. That would be perfectly fine. But that's two equations, and what we're going to do with complex notation is find a way to bring this together into one equation that includes the amplitude and the phase information together. So we're going to start with these two equations, and the first thing we're going to do is to find something called I, which is the square root of -1. So this is what's called an imaginary number, an imaginary quantity. The square root of -1, if you take that quantity and you square it, then you get -1. So this gives us some very interesting behavior. So what we're going to do is we're going to take our two quantities, x and y, and we're going to put them together into something called a complex number. So this complex number is going to have a real part, which is the x, and an imaginary part here, which is represented by y. So the imaginary part is the part that's multiplied times the I, and the real part is the part that it isn't multiplied times the I. And so if I do this, then this becomes a one equation. So with describing with z contains both the x value and the y value. So if I take that circular motion example, then I would write down one equation, which is z is equal to r cosine omega t plus I r sine omega t. So it's kind of like, just assigning unit vectors for the two different directions, but it's actually more helpful than that. We'll see this, it's got some extra benefits than just something like unit vectors. So what makes it really important is this thing called Eulers Formula. So Euler in 1748 showed that you can take cosine theta plus I sine theta, and it will show up, it will actually be equivalent to e to the I theta. Now you can prove this to yourself by just doing a Taylor series expansion of cosine, a Taylor series expansion of sine, plug into this expression and show that you get the equivalent to the Taylor series expansion of the exponential e to the I theta there. So I'll leave that for you to prove, but what's important about that is that then our equation here, which is r cosine omega t plus IR sine omega t, becomes just z is equal to r e to the I omega t. So that makes it even more compact than it was before. And that is actually a great simplification. And one of the ways I'll show you that it's helpful is this simple example here. Let's say that I had this expression, cosine omega at plus I sine omega at, and I wanted to multiply that guy times this guy, cosine omega bt, so a different frequency, plus I sine omega bt. Now, if you didn't know about complex numbers, or at least you just knew about, you didn't know about Euler's formula, but you knew about complex numbers, if you were going to do this calculation, what would you do? Well, you would just distribute it and you would multiply this out, and you end up with 4 terms like this. And you think, oh gosh, that's a lot of work now, because what I'm going to have to do is I'm going to go look up my trig tables, and I'd go to my trig tables and I'd find these definitions for how these products can be combined into these sums and differences of cosines and sines with different arguments there. And then you would do all this substitution in here, and you would finally simplify this guy back down to cosine omega A plus omega B times t plus I sine omega A plus omega B times t. So working with the transcendental functions, the cosine and sine, you can see that this is going to be a little bit of work, but you can work through it. But if you were just using Euler's formula, you would have right away realized that this guy is just e to the I omega AT, and this guy is e to the I omega BT, and clearly that's obviously just what the rule for exponents is just going to be e to the I omega A plus omega BT, which then you can re-expand out as the result that we got before. So I know this might seem like a simple example, but when you're using complex numbers, it helps you avoid a lot of sort of unnecessary trig modifications that you need to do in order to get to another simple answer here. So again, this is really helpful. So when we talk about complex numbers, then some more jargon here, but we talk about the complex number, we also can write it in this form. So x plus iy is also equal to the magnitude of the complex number, which I'll use the magnitude symbol here. So z times e to the I theta, where z is the magnitude, which is just the square root of x squared plus y squared, and theta is the argument of the complex number. So theta is just equal to the inverse tangent of y over x. All right. Now another important thing is what's called a quantity called the complex conjugate of a complex number, and that you obtain by taking the imaginary part and changing its sign. So if this is a complex number, then we'll use a little asterisk up here to represent the complex conjugate of that number, and that's equal to x minus iy. So that operation is very useful, and you can imagine if you were doing it with the Euler's formula, you could write e to the I, you write z is equal to magnitude of z e to the I theta, and then the complex conjugate is just the magnitude of z times e to the minus I theta. It's another way of doing the complex conjugate. And so if you're using these complex conjugate, one nice way to use it is if you multiply a number times its complex conjugate and you take the square root, then you'll get back the magnitude, and you can sort of prove yourself that here. If you just multiply this guy all out, you can see that you get the same value. And another useful thing will be that if you take a number of complex numbers that are multiplied together and you want to take the complex conjugate of the product, then it's just the product of all their individual complex conjugates. And that's all I think we want to do here. Next we'll go on to looking more into the wave chapter. So that's it for this short video.